Okay, I think it's okay. At least that works. Yeah. Okay, and then let me continue. Okay, so welcome. Okay, so let me start very quickly. I mean, I think you know who I am. You have seen the title of the course, and then I think you have even seen like what topics I want to cover. So I don't think I have to say much. This is the plan for today. Like what about the topics I want to cover? Well, I want to start with some very basic hyperbolic geometry, and kind of with the very minimum in order to arrive at the Ptolemy's identity in the hyperbolic plane. So let me say only a few words about this. So I think you all know Ptolemy's identity for the Euclidean plane. So let's say that I have a circle in the Euclidean plane. So a Euclidean circle, and I have an inscribed quadrilateral, and it can be any. Yeah, and then let me draw the two diagonals, and let me call them, the diagonals, I'm going to call them K prime, and I don't know, let's say A, B, C, D, and then the lengths of those Euclidean segments satisfy the identity, Ptolemy's identity, which is xk times xk prime equal xa xc plus xb xd, right? And I think I mean this is classical geometry. So I'm going to start with the hyperbolic geometry from scratch. So from Möbius, from just the notion of Möbius transformation of the Riemann sphere, and develop the basic tools in hyperbolic geometry to be able to state this identity, but in the hyperbolic plane. So of course, it has to be appropriately stated, right? I mean, I have to really find these quantities that are going to play the role of these lengths. Okay. Then in the end we are going to see that kind of we've done some work already to relate the hyperbolic plane to the notion of continued fraction, and then we're going to see that for a continued fraction, one can define certain bipartite graph that gives you the expression of the whose perfect matchings give you the expression of the continued fraction. And then after that, so this is kind of how do you say, an interlude. This is some sort of interlude. And finally, the definition of cluster algebra. And then we are going to see that the perfect matchings of the bipartite graphs that appear here are very useful in cluster algebras. Now I choose this way because if you go to just Fomin and Celebinsky's papers on cluster algebras, then you find the notion of mutation, and it's like this is the notion of mutation of matrices, yeah, and then the notion of mutation of clusters, where this is not a complex conjugation. This is something else. This is like a z bar is just a new variable different from z. But then you say, okay, but what, I mean, right? I mean, like, what does this mean, right? I mean, what does this formula mean, and why would this be interesting, right? I mean, and why has this been somehow trendy in the last like 23 years in several areas of research? I mean, this looks so strange. So somehow the idea is to see that in certain very nice contexts, one arrives at this formula in a more or less natural way, because if you look at this is the product of two things equal to the sum of two binomials, and the binomials look kind of very ugly, but of two monomials, and the monomials look very ugly, but they are still monomials. And what we are going to see is that in this context, the monomials are actually just very simple monomials. So that's it. And then if time permits, I want to interpret this Ptolemy identity by kind of the hyperbolic version of this Ptolemy identity. I want to interpret it as giving a change of coordinates for certain coordinatizations of certain Teichmüller spaces, as in Professor Tomasi course. But we're going to, it would be a slightly different version of Teichmüller space. It would be a decorated Teichmüller space. So time permitting, I'm going to interpret this as a change of coordinates for coordinatizations of that space, of Teichmüller space. And some references. So, I mean, I'm a person of many references. So, yeah. Okay. Yes, these are many references, I know. For the first part, I think Anderson's book is enough. I find this book really beautiful, and I think it will be enough for the first part. Then for the part on continued fractions, these, I would say, striking papers by Cianacci and Schiffler, who were the ones who found the relation between continued fractions and cluster algebras via those perfect matchings of bipartite graphs. Yeah. And then for cluster algebras, I mean, this is the one that has like all the information, although it's I would say a kind of dense paper. So I would probably, for an introduction, I would just probably go to Lauren Williams's survey. Yeah, and time permitting. And then for the hyperbolic version of Ptolemy's identity, it would be this paper by Nakanishi, or this preprint or book by Robert Penner. Yeah, Robert Penner was somehow the one who first realized that, if I remember correctly, the one who first realized that Ptolemy's identity holds also in the hyperbolic plane. Okay. Yeah. So something that kind of I'm just copycatting. I mean, I'm just copying George. And somehow, sadly, in my other course, in the course on homological algebra, I'm completely failed. I mean, it's been already 2 weeks or 3 weeks that course started, and I'm the only one who has written something in this Padlet platform. Yeah, but okay. But so here, I hope that I'm not the only one who does it. I know I'm not going to be the only one, but I hope that it's not only the usual suspects. Yeah, and then the password Grappolo is because I asked Salvatore Stella what should be the translation of cluster algebra to Italian, and then he told me that kind of to him the most natural would be algebra a grappolo, and I liked the name. So now, yeah. So now, I mean, when I speak Italian, I try to say algebra a grappolo instead of cluster algebra, or algebra cluster. Yeah. So this is going to be an interesting exercise. Yeah. So let me start very quickly with the Riemann sphere. You know, in the end, Möbius transformations are transformations of the Riemann sphere. For those who know Riemann surfaces, Möbius transformations are precisely the automorphisms of the Riemann sphere as a Riemann surface. But I said that I will speak like from scratch. So, so very briefly, the three incarnations of the Riemann spheres of the Riemann sphere that I know are the one-point compactification of C by just adding a point at infinity, where C I take it with the analytic topology, so the topology coming from the norm, and then this one with the one-point compactification topology, which whose open sets are either the open sets of C or the complements here of compact subsets of C. Okay, so that's the topology. Another incarnation is as the projective as the complex projective line. So that as a set is its points are the one-dimensional C vector subspaces of C2. And again, here, what topology do I take? I know that I can obviously take you know, the Zariski topology, but I'm going to be taking also the analytic topology. So I endow C2 with the analytic topology, and then I have this orbit space. So I just put the identification topology for this one, identification topology of the analytic topology. So that's the one I'm going to be working with. Yeah, and the most visual one, the unit sphere in Euclidean space. And then, of course, they are actually three kind of models of the same Riemann surface. So there are transformations between them. Actually, you know, diffeomorphisms, conformal diffeomorphisms, and kind of better said, there are just Riemann surface isomorphisms. Yeah, of course. Right now, I have not told you what their complex atlases are, but I can tell you some words about the these transformations. So, for instance, this one is interpreting C bar as homogeneous coordinates. So this means that Z in C, let's say Z in C, goes to the vector subspace spanned by just Z1. And the only other point missing goes to the only other subspace that I haven't covered yet with the other one. Yeah, so that's phi. I'm sorry. Excuse me. Switch. Sorry. Yes, you are here. Yeah, thank you. Yes, 1-0. Yes. Yes. Sorry. Yeah. Otherwise, that was not even bijective. Yeah. Okay. this map is just like just realizing that in any vector subspace whose second entry is non-zero can be represented has a vector of this form, and then what you do is you just take any element of that vector subspace whose second entry is not zero, and then you just divide by that second entry. Yeah, and then there's only one vector subspace whose vectors have zero in the second entry. Yeah. So these are these two, and then these two are the stereographic projections, which I'm going to denote P and Q. That I'm not going to give the formula. I'm just going to say that they are. I take the stereographic projections from the North Pole, where I see C bar, at least the finite part, C, I see it as the XY plane sitting horizontally and kind of crossing the equator of the sphere. Yeah, and then these are just these stereographic projections that you are seeing here. In this one, in this picture in the middle, what you are seeing is somehow like you see the image of a point here, like the image of this interval is this circle segment, yeah, for example, and that's what you're seeing, right? So the image of this very long straight interval is just this circle segment, etc. Yeah. By the way, a good exercise is to see what are the transformations here that make the diagrams commute, right? And then I like try to do it directly. Of course, I can compose, but try to do them directly, or compute the composition and try to interpret that as something defined directly. That's a good exercise. Okay, now I'm going to be mainly working with the C bar, and I'm just going to resort to the other two models, namely P1C and the unit sphere when it's convenient for me. So we defined the notion of circle in C bar, and it's a very simple notion. It's either an Euclidean circle in the complex plane, or the union of an Euclidean line with infinity, thinking that somehow a straight Euclidean line kind of passes through infinity. So I call it a circle. A disk is a connected component of the complement in C bar of a circle. Right? So a circle in C bar always splits C bar into two connected components. Each of them is just called a disk. And then a proposition which is not hard to prove is that the stereographic projections send circles to circles. So circles in C bar are sent to circles in the sphere, and conversely, circles in the sphere are sent to circles in C bar. There is one easy instance of this, which is, for instance, if you start with the circles in C bar that pass through the North Pole, then their image is just a straight line union infinity, because you have to take, because you have your circle passing through the North Pole, so there is a plane cutting out that circle in the sphere, and that plane, contains all the lines that give you the stereographic projections of the points in the circle, and it's a plane, so the image is just the intersection of that plane with the horizontal plane. So at least for the circles passing through the North Pole, it's rather easy to show that their images are circles in C, and it's the other ones that become a bit harder. I'm going to skip the proof, but it's not. I mean, it's really a routine exercise. And in any case, if I'm not mistaken, Anderson's book has a proof. Yeah. So now let's start with Möbius transformations. Now the definition I like is that a Möbius transformation is a map from P1C to P1C induced by, is the map from P1C to P1C induced by a bijective C linear map from C2 to C2. I mean, P1C is a topological quotient of C2 minus the zero vector. So if I have a bijective linear map from C2 to C2, it of course sends one-dimensional vector subspaces to one-dimensional vector subspaces. So it induces a map, a unique map from P1C to P1C. That's the definition I like. Because, for instance, you can see immediately that it is at least a homeomorphism of P1C, because it was induced by a bijective map. Now, when you translate that definition to C bar on their homogeneous coordinates of P1, the ones that I mentioned some minutes ago, this is the formula that you obtain. So the fact of this division amounts to precisely the division that I mentioned, where you say, okay, if a vector subspace has a vector whose second coordinate is not 0, divide by that second coordinate, and somehow this denominator amounts to that division. That's one of the reasons I like it. It kind of it demystifies Möbius's formula. So Möbius's formula is kind of no longer so magical. It is, right? But yeah, and then here you see, then you can tell me, okay, but there's, how about minus C divided by D? This one gives you 0 in the denominator. Yeah, but then I think I just define, if I take a non-zero complex number, yeah, so that for this is that I have here on the right. So for a non-zero complex number, so C cross is just C minus 0. W divided by 0 is just infinite. And there is no ambiguity. And then you can also say, okay, so how about infinity when z is infinity? And when z is infinity, I just follow, I don't know, it's calc 1, where one proves that when the variable goes to infinity, what you obtain is just the quotient a divided by c. Right? So I just follow that rule, yeah, which I must follow if I have any hope of making this a continuous function from C bar to C bar. Okay, so in other words, let me here just write, mu a of infinity is a divided by C. Yeah. Here, of course, I'm assuming that the matrix of these coefficients has complex entries and is invertible. Yeah, why? Because I'm thinking about bijective linear maps from C2 to C2. Okay, an easy check is that taking mu of a matrix is a morphism of semigroups. In other words, mu of a product is precisely their composition. That's a very easy direct computation with this formula, or a bit more elegantly, if you see this as the shadow of a bijective linear map from C2 to C2, this is just the fact that the matrix of a composition is the product of their matrices, and then shadow of that is this, as well as this other identity. Yeah, and this is always a self-diffeomorphism of C bar. Yeah? And actually, not only a self-diffeomorphism, it is actually a conformal self-diffeomorphism, and it is a conformal self-diffeomorphism because it is actually a holomorphic function from C bar to C bar. With non-zero derivative, with non-zero complex derivative, with non-zero derivative. Okay, now we denote by this Möb plus C bar the set of all functions that are Möbius transformations. Okay, just this. This plus is just it has to do with this orientation preserving that later we will mention some transformations that are not orientation preserving. Yeah, so just in case I mention that, then I will probably use this notation for that other notion when orientation is not preserved.
This is
right. Yes.
Is it a portion?
Yes. So the thing is, I have the function that goes from GLC to this set of functions that I just defined, which is, by the way, closed by composition because of this, and closed under taking inverses. Yeah. And this is actually a group homomorphism, and its kernel is precisely the set of all non-zero scalar multiples of the identity. In other words, two matrices induce the same Möbius transformation if and only if one is a non-zero complex multiple of the other. And so one defines PGL2C, one defines it as the quotient GL2C modulo this, yeah. And then what happens is that this is just isomorphic to PGL2C. So it's like a this I would think that this is some sort of concrete incarnation of this, if you want, abstractly defined group. Okay, so indeed they form a group. Yeah, and there are some standard examples, some easy examples. Unfortunately, we are going to see that that up to conjugation, it is possible to kind of reduce the study of the geometry of every Möbius transformation to the study of the geometry of the easy examples, which I'm just calling standard examples. The first standard examples are the translations that by definition fix infinity. So I take a translation of the plane of the complex plane by a non-zero complex number. I decide that infinity is fixed because otherwise I don't have a I lose bijectivity, so I have no option. And this transformation is easily seen to be the Möbius transformation associated to this matrix. This is really easy, because this zeta plus beta is equal to zeta plus beta times 0 z divided by 0 times zeta plus 1, obviously. Yeah, so this is a Möbius transformation, and I notice that it has exactly one fixed point, namely infinity. Translations. I mean, when beta is not 0, right? So let's see. Yeah. Let's say here, of course, if beta is not 0. In other words, if the translation is not the trivial translation that doesn't do anything. Okay. It has exactly one fixed point. Well, it happens to be the trivial translation. Well, if and only if the complex number here is 0, obviously. And another obvious computation, the powers of the Möbius transformation are given in terms of the powers of the matrix. That's just the previous lemma that it opens products and of matrices, and this is all, and this power is like a super simple exercise. Which if you think, yeah, of course it has to be the end power has to be translating by beta n times, of course. Now, what properties do this have? I mean, there are some obvious properties. The first property is that if I consider the family of all Euclidean straight lines parallel to the translating vector, each of these lines is stable under the action of the whole subgroup of Möbius transformations generated by mu A. So each of these is obviously stable under all these powers. Okay. So we have all those. I don't know if I don't know if it's the correct terminology, but I like to call them, the stable curves. But I know that this is probably not the right choice of terminology. Okay. Anyway, and then for any vector not parallel to the translating vector, if you consider the family of Euclidean straight lines parallel to this new vector, which is not parallel to beta, what happens is that translation by beta permutes this other family. So what we see is that we obviously find at least two families of curves that have certain properties. For one family, each curve is stable under the action of the whole group generated by the Möbius transformation, and for the other family, which can be chosen in many different ways, but this other family, I mean, depending on which non-parallel vector you choose, but this other family, once you fix the non-parallel vector, is permuted by the group generated by the Möbius transformation. Moreover, if you delete the fixed point from C bar, each of these two families foliates C bar minus the fixed point. So in the first case, the family of straight lines parallel to beta foliates C, and in the second case, if you fix a vector not parallel to beta, the straight lines parallel to this new vector, also foliate C, which is C bar minus the fixed point. Okay. There is another obvious type of example, which is just multiply, in C bar, just multiply by a non-zero complex number, and then of course you just fix infinity. That's obviously the Möbius transformation associated to this matrix. Now, if alpha is not one, if alpha is not 1, if alpha is not 1, there are exactly two fixed points, namely 0 and infinity, which is obvious. Okay, for this matrix, the associated Möbius transformation is the identity, if and only if, well, alpha is just this multiplication by 1, also obvious. And finally, the computation of the group generated by this Möbius transformation, well, it's just the Möbius, the nth power is just the Möbius transformation of this matrix, which is obviously multiplying by n times, well, is multiplying by n times, right? I mean, so this is kind of practically tautological. Okay, but now something is going to happen, which is that we have to beware, of where alpha sits. And then we're going to later see that what happens, what is. Okay, now I'm going to divide the analysis of multiplication by alpha in cases, and later what we're going to. I'm going to do that, and this I didn't do in studying translations. And what we are going to see is that what happens is that every Möbius transformation with exactly one fixed point is conjugate as a Möbius transformation to a translation, and all translations are conjugate to each other. But the same does not happen for multiplication by alpha. For that, and that is the reason why we have to divide in cases the study of these easy Möbius transformations. And now that division into cases is according to this partition of the non-zero complex numbers. I mean, alpha is a non-zero complex number, yeah. And then, of course, I don't want to somehow I take for granted that the study of the identity Möbius transformation. Right? Yeah. So here, yeah. So I'm going to omit this, and then the rest is going to be these three sets. So which is, according to whether alpha lives in this union of two open segments, or in this kind of open segment of the circle. So the circle minus certain point, or the rest. So on all this other dense set. And the geometric behavior is going to be classified according to that. So let's start with with this one, which is multiplication by some positive real number, different from 1. Yeah, I'm going to take it different from 1. So here I should maybe say different from 1. And then I don't notice this. I'm going to start also with obvious obvious observations, and here I should do this. Again, obvious observations. If I'm multiplying by a real number greater than 1, then of course, whenever I take any non-zero complex number, and I start multiplying repeatedly by alpha, of course I'm going to the complex number is going to become bigger and bigger and bigger and bigger, and the limit is just infinity. Obvious. Also obvious if on the other hand the real number is less than 1, then the limit of multiplying by alpha repeatedly is 0, no matter what complex number I start with, which means that it doesn't matter what complex number I take. In case alpha is greater than 1, somehow infinity is an attractor of all the iterations, and actually, from this one can also see that when n goes to minus infinity, if alpha is greater than 1, when n goes to minus infinity, I approach 0, which means that really 0 is a repeller if alpha is greater than 1. And the other way around if alpha is less than 1. Okay, obvious observations. And now I'm going to look for my two families of curves that have a certain nice behavior. Yeah? Because that's the behavior I'm going to pull under the conjugation to the other Möbius transformations. And the thing I notice, it is obvious that if I take an open Euclidean ray from the origin, it is preserved by multiplication by alpha and by multiplication by alpha inverse. Which means that every open ray from the origin, but of course not containing the origin, so that's why I say open, each of them is a stable curve for the action of the whole group of Möbius transformations generated by mu alpha. Okay, obvious. And second, of course, if I take a circle and then I multiply it by alpha or by alpha inverse, its image is another circle, of course, centered at the origin. Right? So the family of circles centered at the origin is permuted. Yeah. Okay. Next obvious observation, each of these two families that I just mentioned foliates C bar minus the fixed points, because the fixed points are 0 and infinity. By foliates, I mean that that every point in C bar minus those fixed points lies in exactly one curve of the family. Okay, and moreover, these two families, in this case, they are orthogonal. They are mutually orthogonal. If I take any member of one of the families and any member of the other family, they are orthogonal. Okay? So same thing. So again, I have one family of stable curves and another family of permuted curves. Yeah? And they have the nice property that if I take any and I take any, the angle is always the same, namely 90 degrees. Okay. Now I move on to the next one, which is multiply by an element of the circle. Again here, alpha different from 1, and I'm going to do the same very easy analysis. Now I'm going to I notice that multiplying by alpha then is just rotation, which means now that if I take a circle center at the origin, it is stable under the whole subgroup under the whole group of Möbius transformations generated by multiplying by my alpha in the circle. Okay, the set of circles centered at the origin again foliates C bar minus the fixed points. And if I take an open ray passing through the origin and I multiply it by any power of alpha, what I obtain is another ray through the origin, which means that now the open rays from the origin form a family of curves that is permuted under the subgroup generated by the Möbius transformation multiplying by alpha. And again, I have my easy observation that these two families are mutually orthogonal. So any member of one family and any member of the other family are orthogonal. Okay. So, I mean, I find it really nice that these are really obvious observations. Yeah. Now, in this case, it's a bit more complicated, and then maybe the families are a bit. I don't know. Maybe it's arguable whether it's also so obvious to observe as in the previous cases. But you see, now take a complex number here, yeah, and then of course here I'm already excluding 1 because here number 1 is here, yeah, and express it, in polar form, yeah, and what we are going to do is for each member of the circle we are going to define certain curve, yeah, so. It's a family of curves parametrized by the circle, and then each curve is is simply gamma s of t is taking alpha to the t and simply multiplying it by s. So it's quite easy. And then here's the kind of the entirely explicit formula, if you really want to say, okay, what is alpha to the t? Okay. Now, how does this look like? So, my alpha is fixed. It's a fixed. I took it fixed because I'm multiplying by this fixed complex number. And then the form of this is this is easy to see that it looks like a spiral, and it's like it just keeps spiraling, and the spiral gets away exponentially fast from the origin, if the norm is greater than 1, if the norm of the number is greater than 1, and the other way around if it's less than 1, and you see greater than 1 or less than 1 just simply tells me the sense in which it spirals towards the spiral towards 0 looks like. So like this looks like clockwise the way I drew it, and then this looks just counterclockwise. Yeah, and then you see the point is if you have one of these curves, yeah, then multiplying it by different s's gives you the different curves gamma s, and the picture of the graph is simply take the picture you already had and rotate it. You see, so if you have one curve, let's say for s equal to 1, you have certain curve. If you draw it, then you can draw all the other ones by taking your drawing and just rotating it. Yeah. Okay. And now the thing is, This is how it would look in the unit sphere. If you go through the stereographic projection, yes, thanks. These curves are called loxodromes, and the property they have is that if you take any if you take any circle, if any Euclidean circle centered at the origin, any two, and you look at the if you take any two circles centered at the origin and you look at the angle the curve forms with each of them, this angle is always the same, no matter which circle you take, and no matter which curve you took, because they were just translations of each other. Yeah, I have some animation that I will try to bring on Friday about how these curves look like. Okay. And yeah, so there's this statement. Yeah, I just said it. If you take one loxodrome and you take any circle center at any two circle center at the origin, the angles are always the same. In other words, if you consider the family of loxodromes that I just defined, where you let your S vary in the circle, and the family of circles centered at the origin, they are not mutually orthogonal, but the angle between curves in one and curves in the other is constant. It's always the same. And they both again foliate C bar minus the fixed points. So we still have that property. But you can also change, and then still take the family of loxodromes, and now instead of the circle center at the origin, take the straight lines passing through the origin, which are the circles in C bar passing through the origin and infinity. And they again, the loxodromes and this other family has the same property, that the angle between any and any is always the same, is constant. And this other family is also permuted. Yes, and then what else have I not said? Yeah, and then the obvious thing one obvious thing that I have not said is that once you have found one of these curves, of course, multiplying by alpha lies again on the curve by de Moivre's formula. So in other words, like once you have found the curve, you can easily see that is stable under the action of the group generated by the Möbius transformation multiplication by alpha. And coming up with this curve actually is not so hard, right? Because if you start with saying I want a curve which is invariant on their multiplying by alpha, then you say, okay, let's say I start in the obvious way. I take 1, multiply by alpha, multiply by alpha, multiply by alpha, multiply by alpha. So at least you know that in the integers it has to be alpha to the n. Okay, take alpha to the t. Yeah, and then the next, so you have one curve. Okay, next obvious thing. Okay, rotate it. Yeah. So actually, this is an obvious analysis as well. Yeah.
Sorry.
Yeah.
So you said this thing about the constant angle. So if you take a family of loxodromes, so the angle with the circles is constant for each given family, right? So it will depend on
Yeah. If you change the alpha, the angle is another one.
Right.
Yeah. So here I'm using
So
the
it
fact that
depends on alpha.
it depends on alpha entirely. Yes. Yeah, and that's the animation I have programmed. But if I try to do it live now, it's going to be a disaster. So I have to prepare it from home. Yeah. Precisely, kind of to see first that the angle kind of you can easily see that it's really the same, at least visually, and then how the angle changes if you change alpha. Yeah. All right. What else? Yeah, sorry. Before going there, so I have my basic analysis of the geometric behavior in some obvious examples, namely translations and multiplication by non-zero complex numbers. And somehow the I would say the wonderful thing is that these examples suffice in order to study all the geometry of all Möbius transformations. Like, this I find a very remarkable fact, that which it is my intention to see. Now, Möbius transformations map circles to circles and disks to disks. And by what I mean by that is that the image of a circle is always a circle in C bar, and the image of a disk is always a disk, a full disk. Okay, but yes.
Can I ask a stupid question, even though it's an exercise? Is it what is not immediate? So if it sends circle to circles, it ends.
Yeah, if it is immediate. I mean, it's because of by continuity. Yeah, if it sends as if you take a circle and its image is a circle, then disconnect. Yeah, and then connected component has to go to one of the two connected components. Yeah, so
I thought that was something.
No.
Yes.
Yeah, no. Now, what is interesting is to determine which one of the two.
Okay.
Yeah, that becomes, you have to respect the orientation. You have to take 3 points, and then you see, and then you ask, okay, are they? You order them clockwisely and look at their image, and then their image, you have, in order to see where this disk goes, you have to look at the disk that has them in the clockwise. Yeah, that's a bit more tricky, but otherwise, yeah, that is. But yeah, the thing is, it's obvious once you show that circles go to circles. Yeah, and it says 16 and over 30. Yeah. Yeah, it doesn't worry me too much. It's really easy. It's a division into cases. Well, okay, it depends. I think I don't quite remember, but there are some books that really do the entire computation. That if you have something that satisfies the equation of an Euclidean circle, then the image, and then complete squares and so on. I think some books do that. That's the long road, and there's the easier road. Okay, two cases. One is when the gamma in my matrix is 0, in which case you can, in which case the Möbius transformation is just given by this formula, which is multiplication by a complex number and then translation. And those two transformations obviously send circles to circles. The circles don't have to be centered at the origin. And then the other one is case 2. Suppose gamma is not 0. And then what I do is I introduce let me see. I introduce. So you see, I want to say that I introduce a 0. Yeah. So what I do is first I multiply this by gamma in the numerator and in the denominator. Yeah. And then after doing that, I have on bottom I have this gamma, and on top I have alpha gamma zeta plus beta gamma. Yeah. And then after doing that, I add a zero, alpha delta minus alpha delta. Once I do that, I split, and I notice that this is equal to this expression. Yeah. And this expression, so this formula, so the Möbius transformation tells me that zeta goes to this, and you see, this tells me the first thing you do to zeta is you multiply it with gamma, that sends circles to circles. Then you translate by delta, which sends circles to circles. Then you take 1 divided by that, which sends circles to circles. That is left as an exercise. Then multiply by a complex number, sends circles to circles, and then translate, sends circles to circles. So in other words, I wrote the Möbius transformation as a composition of things that send circles to circles, except that I have not proved that z goes to 1 over z, sends circles to circles. Okay, there are 2 proofs of that. One is the classical one given by geometry, which is inversion in the circle and then complex conjugation. That's kind of the classical proof. There's another proof which is if you interpret z goes to 1 over z in the unit sphere, it is actually rotation by 180 degrees along the x-axis. So in the Riemann sphere, it's just that, and that sends circles to circles, and stereographic projection sends circles to circles. So 1 over z sends circles to circles. Okay. Yeah. So the exercise remains, right? That when you take 1 over z and then you interpret it as a transformation of the sphere via the stereographic projections, that new map is rotation by 180 degrees. The exercise remains, but it's in a way kind of, if you want, more elegant than the other classical proof. Okay, fixed points. Let me see, I have 23 minutes. Fixed points. There are, every non-identity Möbius transformation has at least 1 and at most 2 fixed points. At least 1 and at most 2. Which tells me that if you give me a Möbius transformation with 3 fixed points, then it's the identity. Yeah, which tells me if you give me 2 Möbius transformations that agree on 3 points, then they are the same, because the composition of the inverse of one with the other is the identity. Has to be the identity. Why does it have to be the identity? Because it fixes 3 points. So this one already tells me, this theorem already tells me, if you have 2 Möbius transformations that agree on 3 points, then they have to be the same. Okay. Now the proof is basic elementary algebra. So the first thing is we notice, we said that mu a of infinity is a divided by c, right? And then we said division of a non-zero complex number by 0 is infinity. So this is infinity if C is 0. A could not be 0 because, sorry, not C, gamma. Sorry. Yes, also alpha. Alpha divided by gamma. Okay. Yes, gamma and alpha cannot be simultaneously 0 because it is invertible. Now, infinity is okay. So this tells me that infinity is a fixed point if and only if gamma is 0. So if gamma is 0, it is a fixed point. But then if you take a fixed point, what happens is that this one has to be 0 because otherwise you would have a complex number. Okay. Once we notice this, then we divide into two cases. Either infinity is a fixed point or it is not. So in the first case, you know, what we have is gamma equal to 0. So being a fixed point amounts to being a solution of this equation. Yeah? And this equation, so here I have to assume that that mu alpha is not the identity. So that, okay, so this equation, you know, if so I here I made some mistake. Here I have to assume already that that mu alpha is not the identity. Well, which is, if you want, part of the statement of the theorem. Okay. Okay, and then, but then solving this equation, you see, this one has solutions if and only if alpha divided by delta is not 1, and in this case, this is the other fixed point. I mean, the point is, this is an equation of degree at most 1. That's the whole point, which has at most 1 solution. And I can compute it if it's an equation of actual degree 1. Okay. One of the points being that the fixed points are computed explicitly, right? Explicitly in terms of the matrix. That's like one of the points. Kind of one of the points I want to emphasize. Yeah. Now, in the other case, if gamma is not 0, then infinity is not a fixed point. I already justified that. But also, this one is not a fixed point, which is going to be irrelevant for the rest of the argument. But it's a good exercise to see why. Why is this one not a fixed point? It's a nice exercise. It's an easy, nice exercise. Okay. But so since infinity is not a fixed point, finding the fixed points amounts to solving this equation in the complex numbers, because I no longer have to solve it in C bar, because I know infinity is not a fixed point. Okay, and then I realized that this equation, solving this equation, is equivalent to solving this equation, which is equivalent to finding the roots of this polynomial. And then I know the formula that I've known forever. Yeah. So infinity was not a fixed point, and this has, and then there are at most 2 roots, and exactly 1 root if the discriminant is 0. In which case I can compute explicitly in terms of the entries of the matrix, or there are exactly 2, and explicitly in terms of the entries of the matrix. And That's it, and that proves the theorem. Yeah, actually the theorem was proved already here, but then I was stubborn in saying, okay, I can do things explicitly. Yeah. Okay. Simple transitivity on triples of distinct points. So if you see, I'm kind of I forgot the expression. Yeah, kind of trying to get rid of the standard things as quickly as possible. If you give me two ordered triples of distinct points in C bar, yeah, ordered and distinct, but of course, I mean, this means that the W's are distinct among themselves and the Z's are distinct among themselves, but of course, there could be some Z which is equal to some W. That's completely allowed. And then there is a unique Möbius transformation taking first to first, second to second, third to third. Uniqueness, I mean, I already actually saw how it follows from the theorem, from the previous theorem about having at most two fixed points. The only one that, I mean, if something has three fixed points is the identity. If two Möbius transformations have the desired behavior, then the composition inverse of one with the other has to be the identity. So they have to be the same. Okay, now for existence, it suffices to prove the theorem in the special case where the second tuple is the ordered, the second triple is the ordered triple 0, 1, infinity. Why? Because for the arbitrary case, well, first I send it to 0, 1, infinity. Well, I sent the first triple to 0, 1, infinity, the second triple to 0, 1, infinity, and I compose one with the inverse of the other. Okay? So that's why this is enough. Okay. Yeah, I mean, if I prove the theorem in this case, then the theorem is proved in general. Why? Because you give me my two arbitrary triples, and I want to send first to first, second to second, third to third. So what I do is I send to 0, 1, infinity, 0, 1, infinity, compose. Yeah. Okay. Now, and now again, division into cases, because somehow, unfortunately, infinity still has to be treated as a special guest. Yeah? So this is somehow the generic situation where infinity is known of the W's. Yeah? I mean, if you pick them at random, they most likely none of them is infinity. And then, okay, I mean, here, I was supposed to not show this from the beginning, none of this, and deduce it. Okay, and now I'm going to try to hold this like it is, because you see, because I want to send W1 to 0, so W1 to 0. So I take the transformation Z minus W1. Okay. Now I want to send. Sorry. This is that's not true. I want to send. Sorry, it's W2. W2. I want to send it to 1. W2 has to go to 1. Yes. Okay. So I take zeta minus W2. That does the job for W2. For W3, I want to send W3 to infinity. Okay, divide the expression you had that you know that does the job for W2 divided by zeta minus W3. And the new expression, zeta minus W2 divided by zeta minus W3, does the job for W2 and W3. It sends W2 to 0 and W3 to infinity. Okay, but W1 is sent to W1 minus W2 divided by W1 minus W3. not to 0. Yeah, I did. Yes, sorry. I was right about W1. I am sorry. Okay. Okay. The thing is, okay, just switch. Yeah, okay. And that's what this expression does. Okay. Anyway, right, so you want this, and now the thing is, you know that this function does the job, and now you just have to present it as a Möbius transformation. Okay, so you have to find a matrix that represents it as a Möbius transformation. Okay, here it is. Yeah. So how do I get it? Well, I try to get it like this times zeta minus, well, this times this, and then this times zeta minus this times this. That's what I do. That's how I find the matrix. Done. That is when infinity is not one of the points. I have 10 minutes and a half. Okay, and now this is, yeah. So let me do this case. Yeah. Sorry. Second case, infinity is one of them. And then, okay, but which one? Yeah. And then if it's the first one, if it's the second one, if it's the third one. So let me do just the case where it's the first one, and then these two will remain as exercises. But the point is that I'm going to follow the very same simple idea. That I want to send, so what was it? 0, 1, infinity, right? So I want to send W1 to 0, W2 to 1, and this one to infinity. Okay? And W1 is infinity. So I want to send infinity to 0, which means gamma has to be 0. Yeah, okay. So gamma has to be 0. No. I want to send infinity to 0, which means A divided by C has to be 0. So A has to be 0. Alpha has to be 0. Yes. Okay. Now, I know that, and I want to send W3 to infinity. So Z minus W3. And I want to send W2 to 1. I know that Z has to go with a 0 here. That I know, because I know that there is a 0 here. Okay. So I'm not going to bother about that. So let's say, what does this do? This one sends W2 to 1 divided by W2 minus W3. But I want it to send it to 1. So what I do is I just divide by that. So W2 minus W3. And this one does the job, which is presented as W2 minus W3 here, 1 and minus W3 here. Okay, and here you see, what do you see? Right, for instance, there's a 0 here, so this better not be 0, because otherwise the matrix is not invertible. But it's not 0 because W2 and W3 are different. Okay, and then same easy ideas solve this. And this solves existence. This solves existence in the theorem. And then uniqueness was already discussed. Okay. And then the 4 types of Möbius transformations, 7 minutes. Okay, and then kind of the miracle is that every Möbius transformation different from the identity is conjugate to a standard example. So every Möbius transformation is conjugate to either a translation or to multiplication by a non-zero complex number. Okay. Now, this depends on this lemma.
So when you say conjugate, you mean in the group of Möbius transformations?
Yes. 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 Yeah. So conjugate in mob. Yeah.
Sorry.
Yeah. No problem. Okay. Now this uses this lemma, which is not a hard lemma. It says, if you give me a Möbius transformation and it has exactly one fixed point, it has to be one of the ones that you already studied. I mean, we already studied Möbius transformations with exactly one fixed point and this point being infinity, namely translations. We know that they have this property. And then the first assertion says no, it's the only ones with that behavior. And second one, we already know a bunch of Möbius transformations that have 0 and infinity as fixed points, namely those given by multiplication by a non-zero complex number. And the second one says, okay, those are the only ones that have that behavior. It's easy, so I'm going to leave this as an exercise. It's just playing around directly with a matrix representing nu. So exercise. You just have to check that certain entries are not 0. Sorry, certain entries are 0. And with this, the proof of the theorem is quite easy because, for instance, if I have a Möbius transformation here with exactly one fixed point, let's say that nu has exactly one fixed point. Let's say that fix C bar nu. So the fixed points of nu in C bar. Suppose that this is just a complex number W naught. Yes. Then you have this. Then define, I don't know. Let's say phi to be the Möbius transformation given as phi of z equal to. I mean, I just want to send it to infinity and conjugate by that, so that when after conjugation I know it's a translation. So z minus w naught. Which is obviously a Möbius transformation, right? I mean, it is associated to, this is mu of the matrix 1, 0, 1 minus W naught. Sorry, that's not true. Here is the other way around. 0, 1. Yeah. Yeah, and this one, when you consider, phi, so I have to go infinity to W naught, nu, and then go back to infinity. So it's phi inverse nu phi. This is a Möbius transformation that has exactly one fixed point. And this exactly one fixed point is infinity. So fix in C bar of this guy is infinity, which means this is a translation by the previous lemma. Yeah, here I'm using that the conjugating one sends fixed points to fixed points, which is an easy lemma. And if you don't believe me, I mean, you can just compute this directly and you are going to see that this is true. And I do the same for this one. I just conjugate by a Möbius transformation that sends one fixed point to 0 and the other one to infinity. This I already know how to do. I do this. Yeah, and actually I do this and I have a 1 parameter degree of freedom because I can multiply here by any non-zero complex number, and it will still do the job. Okay, so I know how to do that, and then I use the second part of the lemma. Good. Okay, so every Möbius transformation different from the identity is conjugate to a standard example. So what am I going to do? I'm just going to take the standard examples and then take a conjugating transformation, and then just map the geometric behavior to know it here. Yeah. So that's already. I'm already telling you everything. Yeah, what I'm going to do. Yeah, but one can give a precise description of the conjugacy classes, and it's that every two translations are conjugate, which is, I still think of this as a bit disappointing, and multiplication by non-zero complex numbers are conjugate if and only if one of them is the other or its inverse. And this means that the conjugacy classes of Möbius transformations are entirely represented by the closed unit disk minus the minus one if you want to exclude the identity, or just the closed unit disk, because the conjugacy class of the identity is just the identity. Okay, and I'm done. So just humor me just one more minute. A Möbius transformation different from the identity is parabolic if it is conjugate to a translation. It is elliptic if it is conjugate to multiplication by someone in the circle, so conjugate to a rotation. Hyperbolic if it is conjugate to multiplication by a positive real number, so like a positive rescaling. And loxodromic in all the other cases. And I'm done, and there are many exercises. Yeah? It's still many. Okay, 20 exercises. You probably want to start with the last one, which is just watch a 2-minute video, which I find it's a very beautiful video, I find, and then some references. Okay, so 30/30, yes. So see you on Friday, but on Friday it's what we start later. We start at a different
12:30.
12:30. Yeah. All right.
So, do you mind if on Friday we bring lunch?
Yes, of course. Yeah.
Is that okay?
Yeah. And here, I hope it really records.